Hello and welcome to a presentation entitled First Order Differential Equations of Homogeneous Variables. We recall that we previously first order equations of this form, and we note that the right hand side here is a function of two variables, x and y, and previously we saw equations of this form which were of separable variables, meaning the right hand side could be factorized into two functions, each of one variable, x and y respectively. Now, having the equation of this form, the question is, when would you say the function f of xy is of homogeneous variables? Say that f is of homogeneous variables x and y if we evaluate f at scaled variables tx, ty, we get t to the power n multiplied by f of xy. That is, this equality must be satisfied in order for us to be able to say that the function is of homogeneous variables order n, where n is the power of t here. And here is a list of functions which we're going to be required to verify if they are functions of homogeneous variables. But before you attempt that on your own, I'm going to discuss with you number 1 and number 3 to show you how you go on with that. Now, taking number 1, we've got f of x equal to x squared times y plus 2y cubed over x plus y. Now, to verify that, we start by evaluating f at tx, ty, and we substitute on the right hand side here with x by tx and y by ty. And simplifying that, we see that we can factorize the numerator with a common factor, having a common factor t to the power 3, and in the denominator we've got common factor t. And simplifying that, we can write that as t to the power 3 minus 1 multiplied by f of xy. As you can see that the expression remaining here is actually f of xy. And simplifying that, we end up with t squared multiplied by f of xy. So what we notice is that we have got f of tx equals to t squared multiplied by f of xy, meaning that f is a function of homogeneous variables of order 2 referring to the power of t here, which is multiplying f of xy. And turning to number 3, we do the same kind of evaluation at tx, ty, and we substitute likewise. And then we note that in numerator we've got a common factor t squared, and in denominator we also have got t squared. Simplifying that, that takes us to t to the power 0 multiplied by f of xy, which is just as good as f of xy. So what we actually get is that f of tx, ty is equal to f of xy. In this case, the function is of homogeneous variables order 0, but here we just simply call it f is of homogeneous variables x and y. Now we'll be given a differential equation, first order differential equation of homogeneous variables. For example, given a problem like this, to verify, we have to verify whether it's of homogeneous variables and then follow the approach which you're going to see soon to solve this equation. So the question will be, how would we go about determining that solution? So let's say we're asked to determine the unique solution of this equation, and if given the condition y at 1 is equal to square root of 2. So if we expect it or suspect that it is an equation of homogeneous variables, then we've got to start by verifying first. So we've got to do the testing. So this function, we're given the right hand side as x squared plus y squared over 2x. So we start evaluating the function at tx, ty, and simplifying, we get this expression, which we further simplify to get t to the power 0 multiplied by f of xy, which is simple f of xy. So then we would then conclude that this function is of homogeneous variable order 0. Actually, in this course, we're only going to deal with the equations of homogeneous variables of order 0. Then our next step in this case would be to substitute y by scaled x scaled by parameter v. In this case, we would then need to find the expression for dy dx, which we find by using the product rule. And if we differentiate this using product rule, we get exactly this expression. And now, the right-hand side of the equation, we've got to substitute y by what we have declared it to be here, which is vx. And doing the substitution and the simplifying x, as you can see that x is a common factor in numerator and denominator, we get 1 plus v squared over 2v. And now focusing on this expression and this extreme right-hand side, we get an equation of this nature. If you look carefully at this equation, you see that this equation is of separable variables. In this case, variables are v and x. So in other words, these equations we can actually refer to them as equations reducible to separable variables. Now proceeding from here, subtracting v on both sides, we can simplify and get an equation of this form. And transforming this further, separating the variables, we get the equation being minus 2v dv over v squared minus 1 equal to dx over x. And then at this point, we can see now that we can go back and resort to direct integration on both sides, which gives us the following. And each of these integrals, we can see that we've got derivatives of the form ln of f of x which we know that we differentiate. When we differentiate, we get this 1 over the argument f of x multiplied by the derivative of the argument of ln. That's what we've got here and there. So integrating, we get a simple expression like this, which is minus ln of v squared minus 1 equals to ln of x plus c. And simplifying further by multiplying both sides by minus 1, we get this equation. And now at this point, remember we've got to get to a point where we've got to leave y as the subject of the formula. So we need to apply on both sides here e. In this case, if we applying e on both sides here, the left hand side, clearly we're going to get v squared minus 1. But looking at the right hand side, we're going to get e to the power minus ln x plus c. And we need to play around and simplify this, and we get e to the power ln of 1 over x using properties of logarithms plus c, which gives us e to the power ln 1 over x multiplied by e to the power c. And you can set here our e to the power c to be constant k. E is the inverse of e. We'll get here 1 over x multiplied by k, we simply can write as k over x. So that expression ends up being y squared over x squared minus 1 equals to k over x. And having substituted v by y over x, and you can see that v squared here, that's why we get it this way. Simplifying this further, we get y squared equals to kx plus x squared. And now at this point, we're almost at the end of we've finished our integration. All what we need to do now is just to express y as an explicit function in terms of x. That gets us to this form, that y is equal to square root of kx plus x squared. And because of the k here, which is a constant and a determined constant, we would call this a general solution. But our equation here gave us a condition here which says y at 1 is equal to square root of 2. Then that we're going to use to find the particular solution. And now in the presence of this general solution, using this condition, we see that y at 1 equals square root 2 implies that k plus 1 squared, substituting x by 1 here, is equal to square root of 2, which takes us to concluding that k is equals to 1. And then we're now at the position we can now write the unique solution, which comes up as y is equal to x squared plus 1. And this is the unique solution which satisfies the condition given here. Now, at this point, I think you have seen the whole procedure of solving this equation by, first of all, substituting y by vx, and after substituting and simplifying, we saw that this takes us to equation of separable variables. And then at that point, we proceed with our method of solving equations of separable variables. And then we get a general solution, then use our initial conditions to get our particular solution. If you miss something, you can pause the video and go over the example again. And once you've done that and you think you understand, you can now attempt the following exercises. But I would like to call your attention to number 3 and number 4. I hope you note that these are not given in the form dy dx is equal to f of x like in number 1. But then you would have to actually manipulate the expression to get to this form, then check if the equations are of homogeneous variables, and then using that substitution, which we've talked about, that y is equal to vx, then reduce the equation to separate variables and then solve. And very important, you must know that your final answer must be in terms of y and x. V is just a helping variable, facilitate the solution of the equations. Otherwise, at this point, I would like to say thank you for listening. My name is Charles Suwas Van Msipa.